Welcome everybody. Welcome to CS4306 Algorithmic Analysis Lecture 7, and in this lecture I will discuss Quicksort algorithm. Okay, so again I will be using Dr. Lee's slides, so I would like to thank her again. So in addition to the slides, so I will go through the book and some other resources like online resources and my own concepts. Okay, so I like you to go through the slides as well as read the book chapter, please. Okay, so Quicksort is another algorithm for another sorting algorithm. Okay, so although the name is called Quicksort, it is just a name. Okay, but it does not mean that the Quicksort algorithm is the quickest sorting algorithm. Okay, so actually in the worst case, that means big O time, so in the worst case the running time time complexity of a Quicksort algorithm is theta, or with a big O n squared. Okay, so where n is the number of element in the array, and in the average case or best case, I can say the best case, that it has efficiency is theta n log n, so that is equivalent to merge sort algorithm. Okay, so you see that if you go to the books, at the beginning you see that Quicksort algorithm, like merge sort algorithm, it applies divide and conquer paradigm. So that you learn in past week. So actually, since it uses divide and conquer method, so it is an in place sorting algorithms, and so all in place sorting algorithms take a stack, some extra stack, not additional memory space. Okay, so in the divide and conquer part, what happens, so as we know that in the divide and conquer algorithm is that we do divide and then conquer and then we combine, right? So as we see that the Quicksort algorithm is very simple, only a few lines, right? Only a few lines. Okay, where A is an array and it has two index, P and R. Okay, so P is called pivot index and R is the last index. Okay, you can say last index. And you see that Quicksort algorithm, it calls itself. Okay, so and one, or it calls another method that is called partition method. Okay, the partition method, it takes okay, so it returns a value, a q value it returns. Okay, so then it says q value that takes the same array and it passes two arguments p and r. So what is r and what is p we will discuss in this later. Okay, so p is the pivot or pivot element, whatever you see. So usually it is pronounced pivot, or in British accent it may be pronounced as pivot. Okay, so you see that this Quicksort algorithm is pretty simple, right? So it is only a few lines of codes, right? So the only few lines of code, only this part. Okay, and but the partition, this algorithm, it use another methods that is called partition methods. Okay, so what does it do? Actually it returns actually, you see that it returns a value, right? So it returns a value. Actually what value it returns, that we are putting in q. Okay, so that is the position actually where we are dividing, where we are partitioning a given array. Okay, so in order to understand the Quicksort algorithm, you need to understand the partition algorithm first. Okay, so since the Quicksort algorithm is a little bit complicated, so in the most of the books and in most of the lectures you will see that this algorithm will be demonstrated using some real actually array, like a small array, and then it will be demonstrating so one by one with some visualization code. Okay, so the book has some visualized code. So if you go through this, then what you will see that it will be partitioning. Okay, but also in addition to this code, if you do a Google search or in YouTube, if you just search with the keyword quicksort, quicksort is one word. Okay, so then this gentleman, he has shown a good visualization demo. Okay, I would do it in face-to-face class, but in order to save my time, so I just like you to watch this video and then you will understand. Okay, and then another thing is that you see in the online resources there are many quicksort algorithm demonstrated. So if my lecture video and our slides do not fulfill your requirements, so then I like you to watch through other lecture videos available online, because one of this Professor Abdul Bari's this lecture is good enough. So, and there are many tons of videos online about quicksort, so it should not be a problem if you spend some time, and then it will be good. Okay, so now let's go back to our slide. So quicksort, what is this quicksort? Then again, quicksort select the specific value called the pivot value. Pivot value is the central value. Okay, to rearrange the array into two parts. Okay, we partition the array. Okay, so in all the elements, how do we divide the arrays into two sub array? Actually, we select a element that we call the pivot element, and that will be the central. It may not be on the central, but we can say pivot means central element, an element. So all the value on the sub array, left sub array, will be less than or equal to the pivot value, pivot element, and all the elements on the right sub array will be greater than, okay, greater than the pivot element. So that is the process to divide the array. So let us trace quicksort algorithm with this short example. Okay, so initially, okay, so then the question is that where should we initially consider the pivot element? So okay, so any element we can consider as a pivot. We can consider the beginning element or the last element, or any second element, third element, or any element. Okay, so later we will see. So there are some trade-off in selecting the pivot element. Okay, so you can select the last first element or last element, or we will see that I personally prefer to select the pivot element as the middle element. Okay, so we can easily find the middle element of an array, right? So by dividing the array length by 2 and taking the ceiling, taking the floor. Okay, so we can easily find the pivot element, right? For instance, like okay, so if my array has like this number of elements, right? So my array has this number of elements. So if it has n elements, so if we start from index 1, in the book has for algorithmic analysis, the book has started with index 1. Okay, so but in actual array we start with index 0. Okay, so the book has 1 to n, so the middle element, the index will be middle elements n by 2, and if we take floor, right, so that is the middle elements index. Okay, so easily we can find the pivot element, but we can consider any element arbitrarily as a pivot element. For instance, this demo, it says we are considering the pivot element as the beginning element, or the first element is 44, right? So then what will happen? Let us demonstrate that. Okay, so then later what there are multiple ways to select the pivot element. So then this demonstration says later we find the middle element. So what is the middle element? 55, right? Then swap the first element with the middle element. Okay, so swap the pivot element, initially the pivot element, with the middle element. So that means actually we are considering the pivot element at the middle, right? So then now we need to partition this entire given array into two parts, on the left part and the right part. Okay, so the left side, so if my array has length n, right? So length n, so this will be, for instance, 1 minus r, 1 to r. Okay, so this will be from here. Okay, so this will be 1 2 2 3 r, and this one element will be pivot element. And then what will be this element over here? If I say r plus 1 is pivot element, and this will be r plus 2, and dot 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 up to n. So, okay, or we can consider that r is coming over here. So then if we consider r here, then this will be r plus 1. Okay, whatever you say, that is not an issue. Yeah, so then we need to consider the pivot element, so that all elements in the left subarray are less than the pivot element, and all element on the right side is greater than the pivot element. So ultimately then actually what we will get sorted. We will get a sorted list, and what it will do, it will be applied, the Quicksort algorithm will be applied on the left subarray and right subarray recursively until it gets fully sorted. Okay, so what we, in this case, what we will get in the first swapping, at least we will get one element in position, a pivot element in position, right? So now there will be two, you see the two subarrays, left side and right side, that need to be reswapping again by applying Quicksort algorithm. So let us go through quickly this tracing, and then what you will see. So you will see that ultimately after few iterations we will get our sorted list. Okay, so but the since the process is a little bit complicated, especially the partition process is a little bit complicated, because what may happen that we may partition the array inefficiently. Okay, so inefficiently means that will make our algorithm to run in the worst case, that has time complexity big O n squared. So for so what actually before I do this demonstration, actually what I want to say, let us go with a few examples. Okay, with a few types. Okay, so for instance, okay, so let us consider a few cases. Okay, number one, okay, number one cases. So if you have so in the number one case number one, okay, so if I have a list, for instance, I have element 10, 12, 11, 15, 13, 27. Okay, So I have a list like this. Okay, so what in this case I see that all elements after the first element are greater than this element, right? Okay, so that means this part is, all of the elements in this part are not in place, but this element is already in place, right? So if you want to sort it in ascending order, so this part is, this first element is already in place, right? So also in the second case we can consider that if I have, for instance, uh, for instance almost same thing I can consider the same example. I have this, then at least you see the last element case 2, this is also in place, right? So if we want to do ascending order display, ascending order sorting, then this is the last element, it's the greatest element, right? So all the elements from the right side are all the elements of the left side of 27 are less than 27. Okay, so that means it is in place. Okay, so that means it is in sorted in this, and these two elements are in place already, right? But the middle elements are not in place, right? Okay, so we need to solve the middle elements to make them in place. Okay, or another case it may happen that, for instance, I have an array. Let me see, I have an array like we have 15, okay, it's 21, 17, 26, maybe 16, and 3, 5, okay, 1, 9. Okay, I have another list like this. Okay, so in this list what do we see, that at least this element is in position, right? Okay, so whenever we sort this, we see that all of the elements on the left side are less than this 15, this element, and all the elements on the right side are greater than 15, right? So in that case what do we see, that in this case 15 is in place, right? 15 is in position. Okay, but not other elements. So if we apply some process to rearrange this left subarray and right subarray, then we're done. Okay, so that means there may have three at least these three good conditions there, where we will have at least one element in position, right? For instance, but we may have another situation. For instance, we may have 5, 25, 7, okay, 7, 9, actually 6, 20, 20, and something, for instance 10. Okay, so as we see that almost none of these elements are in place, right? So none of these elements are in place, so that means this will be our worst case, one of the worst cases. Okay, one of the worst cases, this will be over here. And another, because no element is in place, and another worst case might be over here. For instance, I have an array with a given array like 10, 11, 13, 25, okay, 29, 30, and so on. Okay, so we see that all of the elements are already sorted, but in ascending order. Here is sorted in ascending order, but we want to sort it in a different order, like descending order. So that means all elements we need to swap, right? All elements need to be in place, to put in right place, right? So this on will be another worst case, right? So that means if my array is completely or mostly in opposite order, that I need to get. So in that case will give us a worst case. Okay, so these are the situation that we may face, and based to our these of situations, so actually our partition will be different, and thus the time complexity of quicksort or algorithm will vary from situation to situation. Okay, so now if we see, now we want to see how do we partition, how should we partition this this list. Okay, so when you do partition this list, what we need to do, I need to have a pivot element, and so that we get two sides. One is the left side and the right side. The left side elements are less than the pivot element, and right side element are greater than the pivot element. Okay, sorry, I got stuck. Okay, so now we want to see how the array is partitioned to get the pivot element. Okay, so now let us trace the partitioning algorithm. So in the partition algorithm, what is our goal? To trace the to have the partition algorithm. Actually, we will get a pivot element, and all the elements from the left side will be less than the pivot element, and all the elements on the right side will be greater than the pivot element. What in case we want to get an ascending order, sorted ascending order. Okay, so in so let item, so they said let item less than or equal to the pivot will be color into purple color. So the purple color is the pivot element. Okay, and items greater than on the pivot element will be on the blue color. Okay, so here, so let us see that these elements, the blue, are greater than the pivot element, and the elements, this is the pivot element, and these purple color elements are less than the pivot element. Okay, so now what initially what it says, so making like this one is up. Okay, so for instance we can consider this up variable, and then you can see the last element as the down, and we need to exchange this. Okay, actually I see that there are multiple ways to do this. Okay, so this is one of the way. Okay, so that what is happening, so this one, so 75 is greater than 33, right? So that means they are swapping, exchanging. Okay, 75 is going over there and 33 is coming over here. Okay, so then, and we need to repeat this. Okay, repeat this, and then so this one, next time this one will be up, and then this one is down. So then what we need to do? Okay, so then we need to move. Initially where was up? Initially this was up, right? So then what we will do? So see, 75 is greater than the 33, this element. Then we need to make a swap, and then what do we need to go? We need to go to right until we find any element that is greater than the pivot element. So this is not greater than pivot element, this is not greater than pivot element, so this will be the pivot element, right? So then 55 will be pivot element. Okay, and then on the same time we are moving this down pointer to the left side. Okay, left side, until we get any value that is less than the pivot element. What is my pivot element? Is 44 my pivot elements. Okay, so that means this one in the next iteration, this one up will go to 55 and down will come to 12. So that is what it is shown here. Up is going to 55 and down is going to 12. And then what will happen at this point? So these two will be swapped, right? So these two will be swapped. Then 55 will go over here and 12 will come over here. So now again what we will do, we have just extend and we need to repeat this process, right? What do we need to repeat? Actually, what is our up and down at this position? You see that up and down are down is 12 and up is on 55, right? That is 55 position, that I got 12. And then at this point up, since we extend this, so then up will go to 12 and then down will come to 15, right? Okay, now again we will see if any element on the right to up is greater than 44, right? So actually is any element on the right side is, you see that is less than 44, and any element on the okay. So actually I see that at this point we got like this element, these two positions, this element are in position. Now we need to repeat this for this part and this part, right? So that is going to 55, 44 is down over here. So I'm going back to that algorithm. Actually what is happening here, so this is the process. Okay, so so if my array is given A array and P is the pivot element, R is size. So then we are, how do we split them? P to I and J to R. Okay, so then all elements in the left side P to I is less or equal to pivot element, and all element on the right side is greater or equal to pivot element, right? So that what we do, increment I until pivot, any element is greater or equal to pivot. Okay, and decrement J until any element is less or equal to the pivot element, and if we find that, then we will solve and repeat until we greater than, we go I greater or equal to J. So that means so here at this position I is greater or equal to greater than J. So we will stop over here, right? Okay, so in this position what we will return? We will return J, right? So J will be this one. Okay, so this one, that means that is the pivot element. Okay, so in order to understand the partition code, actually what I like you to do, actually go through this algorithm. Okay, So let us think that. So this algorithm actually, so this is partition method, right? It is taking an array with p and r and additional arguments, and initially what we are doing, we are saying x equal to a or p, and I equal to p minus 1, j equal to r. So initially just forget about this, just forget about this. Okay, so that go to this, okay, and forget about this. Then what do we need to do? While ai lays actually it will incrementing, right? So incrementing ai greater or equal less or equal to x is our pivot element, wherever we can say pivot element in the beginning or any position. Then and also while a j minus like say j will come from right to left, and a I will go from left to right. Okay, so then until how long we will go? We will go as long as j I is less than j. So how do we break this, stop this? As long as we get I greater or equal to j, then if we get this I greater or equal to j, so then what we will do, we were using a swapping, so like internal swapping algorithm, right? You know that swapping is easy. Okay, so and then how long we need to do this? We need to do this until we get one pivot element in position. Okay, so this is why we need to do another loop. We need to have another loop. So now, so understand this internal first, then apply this okay, what I want to say. So now we apply this while loop. So if you understand the internal part, then you apply the while loop, because we need to continue this process for a while. Okay, okay, so actually in our next lecture we will analyze quicksort algorithm. Okay, so let me see. So you will see that in the worst case the complexity will be theta n squared, and in the best case the complexity will be n log n. Okay, so and as you know that the quicksort is an in place algorithm. Okay, and the best case running time is n log n, but that is not always found. Okay, so that we need to consider worst case is big O n squared. Okay, then what else? Actually this while loop can be implemented actually in different ways. We can say while I less or less than j or something. Okay, you can say while I less than j over here, or we can say while true. Okay, that means true, while true means where this true is coming from, right? So then actually is I if I greater or equal to j, that is break, right? So then from where this true is coming from, actually where, that means I here less than j, you can say over here. This is the condition actually. Okay, so now if we come back to to the sorry, I'm having my computer is delayed. Maybe a lot of programs is running inside, so it's not responding. Okay, and okay, so please go ahead with this slide and read the book and some YouTube videos, and then practice something, and then in the next lecture I will analyze the Quicksort algorithm. Okay, so that the at least few cases I mentioned at the beginning, 5 cases actually. So then actually the complexity of the Quicksort algorithm is mainly depend on the partition algorithm. Okay, so if the partition is efficient, then algorithm becomes efficient, and then if the partition is not good, one of the good partitions, then it will take a long time. Okay, that worst case will happen. So that means the partitioning, unless the partitioning part, the Quicksort algorithm is pretty simple. Okay, but again, one more thing, that please remember that Quicksort algorithm just is name is Quicksort. Okay, it is not the quickest sorting algorithm. Okay, so let me I'm trying to go to the book. Actually my computer is not working. Okay, okay, thank you so much, and I will see you in next lecture.